Okay, so by definition, what is a circular motion? It is a motion of a particle or a body such that its path is circular. So it comes from the definition of circle in mathematics, which is that a circle is a, it's a closed figure lying in a two-dimensional plane, such that any point on that curve, which is the circle, any point on the circle is equidistant from the center of the circle. So accordingly, the definition of circular motion also comes from the same thing. So if a particle or a body moves on a two-dimensional plane, such that its distance from a particular fixed point remains constant, then its path is said to be circular. So the convention we do is we take the plane of motion as our xy plane, and we take the fixed point from which the distance is constant as the origin. So that becomes the center of the circle. And the constant distance from the origin, which is the center, that becomes what we call the radius of the circular motion, and we can denote it with the symbol r. So geometrically now we can represent it like this, that if at a certain point of time a particle lies on the xy plane such that its distance from the origin, so distance is magnitude of, so if this is the position of the particle at a certain time, then magnitude of the position vector with respect to the origin r. Now the particle should move if the particle p moves such that magnitude of r is constant at all times, then the motion is circular with the center at O, with radius equal to capital R. So that motion will, as you know, look like a circular path. Should be something like this. So if at any instant of time t, the coordinates of the particle are x, y, then we can also see that there's an equation of trajectory which is given by the equation of the circle, that x square plus y square is equal to a constant, which is square of the radius. So just make a note up to this point. We'll continue further.
Done, sir.
Yeah. Right. So now we can see from here the equation of the circle, how it works out, that if at a certain point of time, the position of the particle is at x comma y. So if at some time t, the position vector of the particle is x I cap plus y j cap. So the magnitude of the position vector is root of x square plus y square. So this mod r should be equal to capital R, which is constant at all values of t. So that means the root of x square plus y square is r, which is uniform or constant. So x square plus y square is equal to r square. This becomes, as you know, the equation of the circle. Just like in projectile motion, you have a parabolic path. In circular motion, you have a circular path which is given by this equation. X square plus y square is a constant, which is the square of the radius.
So,
Hmm.
sir, is it necessary that it should be that the center should be O always, or
Yeah, because when we describe the equation by this kind of, when we describe the motion with this kind of equation of trajectory, now, we have to by default take the origin of our system at the center. I mean, the way you think about it is the circular motion is already happening. Where to select the origin? Because the reference frame is up to us.
yes, sir.
So we select the origin for convenience at the center, and we take the xy plane as the plane of motion, so that we can write the equation of trajectory quite easily like this: at x square plus y square is equal to r square. If we select the origin somewhere else, then we have a more complicated equation. So to simplify and keep the equation standard, we always take the origin as the center of the circular path. So all the equations, etc., that will follow from this point will be with that assumption that we have taken our origin at the center and we have taken our xy plane as the plane of the motion.
Yes, sir.
So now we will introduce something called angular parameters to describe the motion. Angular parameters or variables. Okay, so these are a set of parameters that express the motion quite simply, in a sort of simplified way. So the first thing in this angular parameters concept is that if you want to describe the position vector of the particle at any point of time, then we can always do it in terms of the radius of the circle and the angle that the position vector is making with respect to the x-axis, for example, because we can use the x-axis as a standard reference axis. just as we are using the origin as our standard reference point, which is the center of the circular motion. So like that, we can use the x-axis as a standard reference axis, such that if at any point of time, the position vector which has a fixed magnitude of r is making an angle theta with respect to the x-axis, then you can see that it becomes convenient to describe the coordinates in terms of theta, where theta is the angle with respect to the positive x-axis. So this theta becomes what we call angular position. It is expressed in radians, that is the SI unit. And the sign convention that we use to describe it is that anti-clockwise is positive and clockwise is negative. So for example, if I say that a particle is in circular motion with radius equal to, let's say, 10 meters, and at t equal to t some time, let's say, theta is equal to plus pi by 6. Find its coordinates and position vector. So then immediately from this information that theta is equal to plus pi by 6, okay, we can both visualize as well as express in terms of values the coordinates, the position vector, etc. You can see that x will become in meters. Yes, that's correct. Okay, so I mean, it's not just about describing position vectors, but this is one of the things that once we know the angular position, you can see that we can find out the coordinates of the position vector very easily from that. So it becomes a way of referring to where the particle is at the given instant on the given circle. To find out where it is, we just basically need the angle. If you know the angle, we know where the particle is. So that's why angle is used to describe the position, hence the term angular position. So this is the first of our angular parameters. Angular position. Okay, now the next parameter we described in continuation here is something called angular displacement. Denoted by the symbol delta theta. So the angular displacement is nothing but the change in angular position. So delta theta becomes theta 2 minus theta 1 in a time interval. So for example, if a particle was located here, some time t1, so this angular position was theta 1. Now suppose it's moving like this along a circle of radius r, and after some time, as let's say reached here at time t2, which is t1 plus delta t, and its angular position has become theta 2, such that the change in angular position is this one, delta theta. So that delta theta is equal to theta 2 minus theta 1. So delta theta is also expressed in radians. It also has the same sign convention. Anti-clockwise is positive, clockwise is negative. So for example, if I ask you find the angular displacement for the tip of the minute hand of a clock from t1 equal to, let's say, so what you have to see is that by how much angle the position of the tip of the minute hand of the clock has moved by from 6:30 to 7:10. That will give you the angular displacement, and in this case it will be a clockwise displacement, so you'll have to refer to it with a negative sign. So just note down the definition of angular displacement and then work out this question. We will discuss it in a moment. So anybody got the answer for this angular displacement?
So minus 60.
Minus 60. Yeah. So the tip of the minute hand would be here at t equal to 630. No? Whereas at 7:10, the minute hand would be here. Pointing to what we call 1 o'clock. Okay. So you know that this angle would be 30 degrees. So from here to here, it has made a total angular displacement like this. So our angular displacement is in the clockwise direction. So it is minus of 120 degrees or 2 pi by 3.
Sir,
Yes.
sir, at 710 it points at 2, right?
It points at
2, right?
Oh, sorry, my mistake. Yeah. It is at 705. At 710, it will be here, right? Two here. So this will be 60 degrees. Correct. So how much it is? It is 180 plus 60. Or okay, so simple concept like this. Okay. Now, next thing we can see in angular parameters, something called angular velocity. So we use a special symbol for it, omega, which looks like a W, but this is a Greek single omega. So angular velocity stands for rate of change of angular position with respect to time. With respect to time. So we define what we call instantaneous angular velocity as instantaneous rate of change of position d theta divided by dt, or displacement divided by time d theta by dt for a very small interval of time dt. Whereas we define average angular velocity as average rate of change of position or displacement with respect to time. And this is expressed in radians per second. That is the SI unit. And with the same sign convention. Clockwise is negative. Anti-clockwise is positive. So for example, let's say a particle moves in a circular path of radius, let's say 2 meters, with a uniform angular velocity of let's say pi by 8 radians per second. So find its angular displacement magnitude of displacement and distance traveled in a time interval of 4 seconds.
Done, sir.
Yeah. So tell me, what is the angular displacement?
So it's pi by 2 radial.
Yes, very good. And therefore, what is the magnitude of the displacement?
So I'm getting it as pi.
Pi by 2 is 90, no? So if something covers an angular displacement of 90 degrees on a circle, what about the linear displacement? It will be the chord which subtends 90 degrees, no?
So that's root 8.
Correct. 2 root 2. Very good. Root 8. So let's say if the particle was somewhere, it did not have started from the x-axis, so I can say that suppose it was here at some time t, and then it's having an angular velocity in this sort of direction, which is uniform. Now omega is given to me uniform of how much is it? Pi by 8 radians per second. But more importantly, this is uniform. So this tells me that d theta by dt, which is omega, is uniform. Further, that will tell me that the angular displacement in any time interval is equal to omega delta t, which is pi by 8 delta t. So therefore, in delta t equal to, we want to find out in 4 seconds,
4 seconds.
angular displacement will become plus pi by 2 radians. So that means after 4 seconds, the particle will definitely reach a position where now the new position vector has become perpendicular to this one, because the angular displacement is equal to pi by 2 at t plus 4 seconds. This is where the particle is now. So in this diagram, the linear displacement or the displacement itself would be which vector? That would be this vector here, the one joining the initial with the final position. So it's the hypotenuse of this right angle isosceles triangle. So this is the displacement. So you can see that the magnitude of the displacement would be r root 2. That is, in this case, 2 root 2 or approximately 2.82 meters in that time of 4 seconds. Because the radius is given to me as 2 meters. Now, what about the distance traveled? The distance would be the path. So obviously in circular motion, the distance will be greater than the magnitude of displacement. It would be pi r by 2, right? Quarter circle. It's traveled a quarter circular arc. That would be, in this case, pi meters.
So we can use r theta also, right? S is equal to r theta.
Correct. You can use that also. Arc length. So distance is the arc length. So that is nothing but radius multiplied by angular displacement. So in this case, it is radius multiplied by pi by 2. So from this, you can see that the angular parameters not only help us to find out the position and things like that, but even things like displacement, magnitude of displacement, you can get a good idea of that if we know about the angular parameters. Now, in this particular question, we have assumed that the particle in circular path is moving with a uniform or constant angular velocity. Now, that may not always be the case. Okay? The angular velocity, that is the rate at which theta is changing with time, that itself might be changing. So the particle can also have in its circular path or circular motion a so-called angular acceleration. So in the above case, of course, the angular acceleration would be 0 because the angular velocity was constant. But in general, So we denote it with the symbol alpha, and alpha is expressed in radians per second square with the same sign convention. So angular acceleration is defined as the rate of change of angular velocity with respect to time. So alpha is d omega by dt. This is the instantaneous angular acceleration. Or average angular acceleration can also be defined as the average rate of change. But more important is this definition for us. And you can see that the sign convention is once again that anti-clockwise is positive, clockwise is negative. So now we can do a comparison of, on the one hand, 1D parameters for motion along a straight line versus angular parameters in circular motion. So here position was described as a single coordinate, okay, 1D position. Here position is defined by angle, angular position. Then displacement became one-dimensional displacement, which is the change in position. Here it became change in angular position. Then velocity is defined as rate of change of linear position with respect to time. Here we have angular velocity, which is this. And then we have acceleration. So in 1D motion, the acceleration is dv by dt, or we can also describe it as d2x by dt square, or v dv by dx. So here we have angular acceleration alpha, which is d omega by dt, which also means that the angular acceleration can be expressed as d2 theta by dt square, or it can also be expressed as omega d omega by d theta, just like this one.
So,
Yes,
so can you give us some on angular acceleration?
yes, we'll discuss it.
Okay. So,
Okay, so also we will see one more comparison, that if we had 1D motion with uniform acceleration, then we use the three standard equations. For uniformly accelerated one-dimensional motion, we had the equations that V is equal to U plus AT, S is equal to,
V is equal to E plus A.
and right, V square is equal to U square plus 2AS. We had these three standard equations, which were derived from calculus. So here also, if we have circular motion with uniform alpha angular acceleration, we can see that d omega by dt, which is alpha, is uniform. So if omega is equal to omega naught at time t equal to 0, then omega will become omega naught plus alpha t at time t. Okay, and angular displacement will become omega naught t plus half alpha t square. So we'll have like the comparable three equations. Okay, just replacing the linear parameters with the angular parameters. And
So the proofs
sorry, come again.
are same as that of linear, right? So the proofs to find the equation are
Yeah,
similar.
exactly. The you can say the derivation is just using calculus in the same way.
Yes.
Or you can use graph also. You can see that your angular acceleration is uniform, so omega versus t will become a straight line graph, and that area under that graph is displacement. So you can prove it that way also. Okay, so now let's look at a question based on this. So a particle starts from rest at time t equal to 0 with, or first of all, it starts from rest at t equal to 0, moving along a circular path with a uniform angular acceleration. So that is, let us say, pi by 9 radians per second square. So we want to find the angular displacement and angular velocity at t equal to 3 seconds, first of all. Okay. And second, we want to find the angular displacement when its angular speed has become 2 pi radians per second. So just try out this question, people. We will discuss. Yes, very good, Kirti. Your answers are correct. Your angular velocity will be pi by 3 radians per second. Angular displacement will be pi by 2 radians or 90 degrees, and therefore so here we have to just understand that because it starts from rest, so our initial angular velocity is 0 at time t equal to 0. And because it's moving along a circular path with uniform angular acceleration, so our omega as a function of time here will become pi by 9t at any time t. And our angular displacement as a function of time will be like this. It's like the equivalent of s is equal to ut plus at square. So angular displacement as a function of time will become pi by 18 t square at any time t in radians. So in radians per second. And also we'll have omega square is equal to omega naught square plus 2 alpha delta theta. So here that relation will become that omega square is 2 into pi by 9 into angular displacement. This will also give us omega n. So now for the first part, see at t equal to 3 seconds, just substitute in this. Angular velocity at that instant would be pi by 3 radians per second. And angular displacement would be pi by 2 radians at t equal to 3 seconds. And when omega is equal to 2 pi, delta theta would be equal to omega square by 2 alpha, or 18 pi. Okay, so this is all very simple stuff. Okay, we are coming to the main important parameters of circular motion. Just a moment. Okay, so I'm sure this question is easy enough and clear to all of you. Now let's move on to the next part of the derivations. or circular motion. So we will look at two important aspects first before we come to things like velocity and acceleration. Look at two important unit vectors. Okay. So important unit vectors in a circular motion. Because whenever we are doing vector analysis, like application of dynamics, that is forces or velocity, acceleration, etc., we need to express the directions of the various vectors in terms of unit vectors. So one is, so that is basically the radial unit vector. We generally denote with the symbol r cap. Okay. But in certain textbooks, you will also see they use the symbol ER. And we use the second unit vector, which is important, is the tangential unit vector. We use the symbol theta cap for that. But in certain textbooks, you will see it is by E subscript T cap like this. So let's understand these two unit vectors, and then we'll understand their functioning in various types of vector analysis. So we are taking a standard coordinate frame for a circular motion where the motion happens in the xy plane. The center of the circular motion is the origin, and we use the x-axis as the reference axis for angular position. So if a particle is located at some point of time at an angular position theta, then at that particular instant, if we draw a unit vector which is pointing along the radius, it is called the radial unit vector. And if we draw a unit vector which is pointing along the tangent to the circle with a positive sense of theta in mind, or it is anti-clockwise. So this in general is called the radial axis. And this direction becomes the tangential axis. So here this unit vector is r cap, this unit vector is theta cap. So if we separately understand how r cap and theta cap are oriented with respect to our coordinate frame, and understand that they are perpendicular to each other, and r cap is a vector of magnitude 1 which is making theta with the x-axis, and theta cap is a vector of magnitude 1 which is making 90 plus theta with respect to the x-axis. So that's how we get the formula for r cap. It is cos theta I cap plus sin theta j cap. So it is a unit vector which points along OP, that line. Whereas theta cap, you will see, will become cos of pi by 2 plus theta plus sine of pi by 2 plus theta j cap. So simplifying this using trigonometry, cos of 90 plus theta, you know, is minus sine theta. And sine of 90 plus theta is cos theta. For a particle at the angular position theta at some instant, the radial and tangential unit vectors are given by this. So it is a unit vector pointing along the tangent to the circle at the point. So this is our radial unit vector. This is our tangential unit vector. For a particle in circular motion with angular position theta at some time t. Okay, so one important thing you have to understand here is that r cap and theta cap are instantaneous. Unit vectors. That is, they are changing with respect to time. They're not like I cap and j cap, which are fixed unit vectors. That's because theta, the angular position, is changing with time. So on its own, they are just two definitions, but we will see that these definitions are important for the description of other vector quantities like velocity, acceleration, and things like that. Hence, it's important to get familiar with these two first. Okay, now next let us look at the concept of position, velocity and acceleration. Not angular, but the linear position, velocity and acceleration in a circular motion. But we will define these terms in terms of the angular parameters and the two unit vectors now. So first of all, we'll see that if the position vector is r at some point of time, with the angular position of theta for that particle at time t equal to t, this is the position, and the radius of the circle is capital R, then we can see that the position vector can be expressed as r cos theta I cap plus r sin theta j cap, because the x coordinate is r cos theta and the y coordinate is r sin theta. See, so we can express the position vector as capital R into cos theta I cap plus sin theta j cap, where that is nothing but the radial unit vector r cap.
R cap.
R cap is a unit vector like this. Theta cap is a unit vector like this. Now, based on this, we come to velocity, which is this quantity. So it's differentiation of capital R into cos theta I cap plus sin theta j cap. So when we perform this differentiation, we can see capital R is constant. So we'll bring it out. So it's differentiation or rate of change of cos theta into I cap plus the rate of change of sin theta into j cap. Now this is where we'll have to make use of chain rule. So if we want to find rate of change of cos theta, we'll have to express it as derivative of cos theta multiplied by d theta by dt. And that is nothing but minus sin theta multiplied with omega. So it becomes minus omega sin theta. And likewise, want to find rate of change of sin theta. By chain rule, it will become derivative of sin theta into d theta by dt. So it will become omega cos theta. So now using these two in this derivation here, we can see that this will become capital R into minus omega sin theta I cap plus omega cos theta j cap. Okay. And further, if we take omega common, you can see we are left with the tangential unit vector minus sin theta I cap plus cos theta j. So we see that the velocity is given by this kind of relation. It is r omega in magnitude, but its direction is along theta cap. So this shows us that the magnitude of velocity is r omega and the direction of the instantaneous velocity is tangential at all times. That is along theta cap. That you know from before about circular motion, that at any point of time in the circular path, the instantaneous velocity points along the tangent to the circle. But this is the proof of that using calculus and vectors. Just make a note of this, people. This is an important derivation.
Done.
Okay, so that's about the velocity. And now, as we've seen in the interpretation, it also gives us a relationship between the speed, that is the magnitude of the velocity, and the angular speed, omega. Okay, so that relationship V is equal to R omega. So this also becomes an important relation. And also in terms of geometry, this shows us that if a particle is located at a position like this, then the velocity vector will always be perpendicular to the position vector with respect to the center, because it will be pointing along the tangent. So at any point of time, this relation holds true between these two vectors. They'll be mutually perpendicular. The direction of R, which is along R cap, and the direction of V, which is along theta cap, will always be okay. So as the particle moves in the circular path from point to point, at any point of time, the velocity is tangential. So you can see that even if the speed is uniform, the velocity is always changing because the direction is changing from point to point. So now additionally, we'll understand two important classifications of circular motion based on this. Uniform circular motion. Or what we call UCM. So that is by definition circular motion at a uniform speed v. So speed is uniform implies that angular speed is also uniform, because V is equal to R omega, which implies that alpha is 0. And therefore it becomes a periodic motion because it repeats itself periodically. Because it repeats in regular cycles with time period. Because V and omega are uniform. Whereas the other type of circular motion we'll talk about is non-uniform circular motion. So this by definition is a circular motion with variable speed. So V is not constant. So that means omega is also variable. Which means that alpha is non-zero. Whereas here you can see alpha by definition is 0 and omega by definition is uniform because it's at a uniform speed. Okay, and therefore this is also a non-uniform circular motion is a non-periodic motion. It does not repeat in regular cycles. So this is something important to keep in mind, the definition of uniform versus non-uniform circular motion and their properties. So just make a quick note of this because next thing we are going to discuss is about acceleration. So when we discuss about acceleration, it's important to be able to classify these two different types of circular motions, uniform and non-uniform.
So done.
Okay, so now let us understand acceleration in circular motion, which will come from the following definition, that acceleration is rate of change of velocity. But we will understand acceleration for each of the individual uh, classifications of circular motion separately. So when we are discussing about acceleration for a circular motion, we will first look at uniform circular motion. In case of a uniform circular motion, get this category first. So in general, acceleration is rate of change of velocity with respect to time as a kinematics definition. But in a uniform circular motion, speed is uniform. That doesn't mean acceleration is uniform, because velocity is changing in direction. Omega is uniform. Alpha is 0. Okay. So when we look at this, we have to execute this differentiation. Now we're just seeing that the velocity vector is given by magnitude r omega into the unit vector minus sine theta I cap plus cos theta j cap. So according to this definition, now omega is uniform. So we have to keep that in mind. So omega will also come out along with r, and the differentiation will apply to this. So it's minus of rate of change of sine theta I cap plus of rate of change of cos theta into j cap. And previously we've understood by chain rule that rate of change of sine theta is omega cos theta, and rate of change of cos theta is minus omega sine theta. So what we now see, that this term will become r omega into minus omega cos theta I cap minus omega sine theta j cap. So we can take the minus sign common, and we'll see that the acceleration vector minus omega we can take common. So we can see it points along minus of r cap. That means it points towards the center. So you can see that this acceleration vector is minus r omega square r cap in a uniform circular motion. We'll come to non-uniform circular motion, but so the magnitude of the acceleration is r omega square, or this can also be written as v square by r, because v is equal to r omega universally. Okay, and the acceleration vector points along minus r cap. That means it points to the center. So hence, as you know, this is called centripetal acceleration because it points towards the center. So the term centripetal refers to that. It points towards the center. So now, understanding this geometrically, you see that as long as it's a uniform circular motion, so the speed is constant. So alpha is 0. We have a UCM. Then at any point of time when the particle is at an angular position theta, the velocity vector is tangential and the acceleration vector is centripetal. It's pointing towards the center. But that, remember, is the case of uniform circular motion only. Non-uniform circular motion we'll see is different. But make a note of this first.
Sir,
Yes.
sir, in non-uniform circular motion, there will be two acceleration, right?
Yes, there will be both the tangential and the centripetal components. So let's, if you finish writing
Yes.
this, let's move on to that. So in a second case of non-uniform circular motion, so what we see in that case is that omega is variable, speed is variable, and alpha is not equal to 0. In fact, d omega by dt is what we define as alpha. So when we come to acceleration, which is rate of change of velocity, that becomes rate of change of r omega into minus sine theta I cap plus cos theta j cap. So we have to use the product rule here. This will become capital R into rate of change of this whole thing. So that we will write as differentiation of first term multiplied by second term plus first term multiplied by differentiation of second term. So when we carry out this differentiation, we'll see that this is by definition alpha, and alpha is getting multiplied by this term, which is nothing but the tangential unit vector. But the second term here is the same as what we derived last time. So this is minus omega cos theta I cap minus omega sine theta j cap. So that is the centripetal component. So this becomes r alpha theta cap minus r omega square cos theta I cap plus sine theta j cap, which is, so it's r alpha theta cap minus r omega square r cap. So you can see the acceleration vector has two components now, one along theta cap and one along minus r cap. So the one along theta cap is called the tangential acceleration, or the tangential component of acceleration. And the other one is called the centripetal component of acceleration. So acceleration is the vector sum of these two components. So magnitude of tangential acceleration is r alpha. Magnitude of centripetal acceleration is omega square r, or that's the same thing as v square by r. So this time you can see that geometrically, when we visualize the acceleration vector at any point of time during the circular motion, it has got the two components, one pointing towards the center and one pointing along the tangent to the circle. So just make a note of this. So in a non-uniform circular motion, the acceleration will have two components. It will have a tangential component and a centripetal component, such that the net acceleration now is neither tangential nor centripetal. The net acceleration vector like this, you can see, will become the vector sum of these two. So it will be like this. So you can see that the magnitude of the net acceleration will become square root of tangential square plus centripetal square, because they are perpendicular components. So again, you see the importance of the radial and the tangential unit vector in these derivations. So that's extremely important. So that was our starting point in the vector analysis, to define the unit vectors which give you the two important directions, the radial direction and the tangential direction. Okay, so with that we conclude today's session, and we have covered the basics of circular motion and the description of all the various kinematics parameters of circular motion like velocity, acceleration, etc. So you can get started with questions from H.C. Verma. You can work out up to question number 16 from H.C. Verma exercise. After which we will come to the dynamics part, that once we have understood the acceleration, how to discuss about the forces and the net force therefore acting on a particle in circular motion. So application of Newton's second law, that net force is equal to mass into acceleration. The acceleration in question being the acceleration of a particle in circular motion. So that's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir.